This video is going to focus on the similarities between Laplace and Fourier. And the motivation behind this video is when we were solving our exercises using Fourier, we're switching between Laplace and Fourier and doing this substitution between S and J omega. And I mentioned on those videos that there are a set of conditions that need to satisfy in order for us to be able to do this substitution. But and I'm going over those conditions right now in this video. So I'm going to present these in two ways, one more descriptive and then a second way a little bit more mathematical. So in terms of conditions, your f of t needs to be a causal signal and absolutely integrable. Then its Fourier transform can be obtained from its Laplace transform f of s by replacing s by j omega. So let's just dive in a little bit on this really quick. So causal, what does it mean, a causal system or a causal signal? It means that all the values of x of t are 0 for t less than 0. And a non-causal system, for example, it's something where you have actually values of x of t for t less than 0. The majority of our physical systems that we use in engineering, especially our circuits, they are mostly causal systems. So we are in good shape here to satisfy this condition. The second condition is to be absolutely integrable. What does this mean? It means that all the poles of your f of s, if they are on the left half of the s-plane, then you're good and you have your integration is going to converge to a value. So what does it mean, this s-plane and the poles being on the left half plane of the s-plane? Just you go back to your s-plane here and you have your imaginary axis and your real axis, and you're going to find those roots of your denominator, which are the poles, and the roots of your numerator, which are the zeros. And we're talking about the transfer function that you have in Laplace. And then you're plotting those poles into this plane, and if the if the poles are on the left half side of the plane, so on this side, it means that your system is stable, and that means that your integration in time is going to converge. Alright, so if they are causal and absolutely integrable, that means that I can do this substitution between s and j omega back and forth. In a more mathematical way, we have the definition of Laplace transform, which is given by this integral of your f of t with this exponential of minus st. And recall that this s, it's actually a complex frequency variable. Alright, so we want to find the definition of causal into this expression that we have here. Remember, causal means that you don't have values of x of t for t less than 0, and that it's expressed on this integration here where it goes from 0 to infinity. So that's your causal part of your system. Alright, so the definition of integrable needs to come from the time domain, and it means that your f of t needs to be less than infinite. And this is related with that Laplace transfer function, or on your s-plane, where all the poles need to be on this left half side of your s-plane, and it's related with the term stability. So your system is going to be stable. And notice that that integration is less than infinity, and that's where the stability comes from. Alright, so the definition of Laplace, we go back to our definition, and we have that s, which is our complex frequency variable, and we know that our signal, our f of t, needs to be causal and integrable. And if that is satisfied, that means now that this integration is going to converge when the real part of your complex frequency variable is equal to 0. Well, if I substitute that 0 over here, then we get our s equal to j omega, and if I substitute this into our integration, you get your integration of your f of t gets to that Laplace transform as long as your real part of that s is equal to 0. All right, so how do I tie these together now with the Fourier transform? The definition of Fourier transform is given by the integration between minus infinite to plus infinite of your f of t times the exponential of minus j omega dt. And again, I want that ft to be causal and integrable. So to be causal, I just go from 0 to infinite, and integrable, I just need to guarantee that this f of t, the integration of it, is less than infinite. All right, so if this is satisfied, if I put both equations here side to side, you will see that they are exactly the same equations, and you see that my Fourier transform can be equal to the Laplace transform, substituting the s by j omega, as long as the real part of your s is equal to 0.